Okay, I think we can start. Please come in. Hello, everybody. So it's my pleasure to introduce today Professor Jiawei Han from the University of Illinois at Urbana-Champaign. You probably are familiar already with Professor Han's, at least his famous book on, Introduction to Data Mining, right? Concepts and Techniques, which in fact just came up with a new edition. I have a copy. But in fact, the book is just an example of these great contributions to the field, because Jiawei is a superstar in data mining and knowledge discovery. And in fact, he has been widely recognized with awards, right? And he has been the founding editor of the journal of the KDD journal. He's been program chair or co-chair of the KDD conference, ICDM conference, and many other events. Of course, he's a fellow at IEEE and ACM. But most incredible is the number of papers that he published. I don't know if you can guess. I mean, those in this room can guess, but basically it's a very high number. I hear a number like 600, which is an incredible number, okay? By the way, today's lecture is dedicated to Dr. Norman Friedman, who is sitting right there. And he was also a graduate from UCLA. He got his PhD in engineering in '57 from this very university. And he went on to occupy very important position in government and in the private business, including chairmanship of the DAISY system and Cordova Corporation. But he never forgot UCLA. In fact, he has been a very generous donor, including, he has been also the donor of the chair in knowledge science, which I have the privilege of occupying. So let's thank Friedman and Dr. Friedman and Professor Han, and give them a warm hand in applause so we can cheer them and tell them welcome. Okay?
Okay, good afternoon, everyone. So it is nice to escape Illinois snow coming down the nice weather of California, especially LA. Actually, this morning I just received an email from my wife that, oh, it's snowing outside, it's pretty heavy. Okay, so, but I show you the picture. This one's in the summer. This is a computer science department called Thomas Siebel Center. It's like Dr. Friedman. We got the previous alumnus is Tom Siebel. He donated to this building, got like $35 million plus another match up of $35 million from state government. So we got $70 million, and this one started using in 2003. We call this one Thomas Siebel Center. Okay, so that's a fortune for computer science, both faculty and students. Because in one department, you get so many, lecture rooms, seminar rooms you really enjoy. So now my talk today is on our recent work on mining heterogeneous information networks. So the title is on the power of heterogeneous information networks. The work actually was done by working together with quite a few students. All these four are my students. Actually, Yizhou Sen is graduating this year. She will be on the market. Mingji and Shi Wang, the newer students, they just the second or third year. Xiaoxin Yin, he got a PhD in 2008. He got actually 2009 the first time, got a KDD's ACMC KDD dissertation award. His dissertation got the first award. So now he's in Microsoft Research. The work actually was supported by a long list. Probably I should mention is Army Research Lab, U.S. Army Research Lab, ARL. They support the center called Information Network Academic Research Center for 5 years. The money actually is more than $15 million for this information network research. So it's really boost, the nationwide research. It's not for this network. I'm taking the lead, but the money actually distributed to 7 campuses. Okay. So I'm going to discuss a few issues. I think it's very exciting, but please feel free. Anytime you want to interrupt me, want me to clarify things, feel free. I do not say you have to raise your hand at the end of the seminar. I think you can discuss with me anytime. The first thing I want to discuss is why the structured heterogeneous information network is very powerful. Okay, philosophically. Everybody knows social network. Even you got a movie, say social networks, probably is also captioned by Hollywood. Okay. But social network got so many things. Everybody knows Facebook, MySpace, or recently Google+. Everything is on the web, your pictures, your relationships. Okay. But people are actually not satisfied with that. You probably see even for presidential election, you got Twitter, people tracing Twitter all the time. Okay. There are so many other social networks like YouTube, everybody knows. So people say mining social network become very interesting, which is truly true. It's rising, it becomes very hot. We are mining on networks, but we are not directly focusing on social networks. We're actually working on mining heterogeneous networks. Then I first want to make distinction on what is the difference between social network and our heterogeneous information networks. Okay. The first thing is most social network actually like a Facebook. They study friends linked with friends. Okay. Then you got like homogeneous network because all the entities, major entities, just friends. You link with friends. But that actually contains lots of diversified information. You can link with your, high school friends, or you can link with your colleagues, link with your advisors, link with even patients and doctors, or there you can link to anyone. But they are very different links. Okay, so some people even study PageRank on Google, web mining or something. But PageRank mainly thinking pages link or pointing to the other pages. It's still like homogeneous. Everybody is a page. It's, you just point to because you endorse this page. You like this page. Okay. But we are studying, we call heterogeneous network. What is heterogeneous? I can give you an example, then you probably think everything almost like a heterogeneous network. Just give you like a medical network. Okay. We got patients linked with doctors or linked with disease, treatments, hospitals, and all these things. Okay? Even patients linked with doctors. You would think patient linked with doctors is different from patients linked with the other patients. They are very different. Okay? The same thing, doctor linked with doctors is different, okay, from doctor linked with patients. Those are heterogeneous because it's different kinds of entities linking with different other kinds of entities. Okay. Then even in computer science, a lot of people try to check papers. You use, say, DBRP or this kind of bibliographic networks or databases. What you do is you say, I look at authors or conference or papers, or I just use some keywords, try to find papers. Okay. You can see your publications actually contain different entities. You contain something like authors, or something like venues, or keywords, or titles, or year. They are different, but they link together. Okay, this is heterogeneous network. Okay. If I say this is a heterogeneous network, you probably say, oh, almost everything is a heterogeneous network. For example, you go to any database. You say, oh, these databases are the courses. You link with the students attending the courses, instructor teaching courses, classrooms, contents. This is a heterogeneous network. Any database, if you map them in a network view, it becomes a heterogeneous network. Okay. So we study this kind of thing. Okay. But we study is different from the typical database, because the typical database is thinking, I'm retrieving data, doing indexing, search, or something like that. We are doing mining, but we view them as a real network. Okay. What's the power we can get? We can get from the entities, from the structures, from their links. Okay. You probably know the linking on web, you get page rank, is very powerful. Then here you think all those things linked together, it becomes even more powerful, which is true. Okay. Let's look at this. I'll give you a typical network. For example, this one is a co-author network. Okay, that means who, for example, we put it in the center is Prof Smith, who is a UC Irvine professor. He happens to be this last year's KDD program committee co-chair. We put him in the center to see who he was collaborating. Okay. But this network actually is a projection of a real publication network, bibliographic network. That means you study co-authors, you get some information, I got more information because I know which paper is co-authored with who, publishing which conferences, and using what kind of keywords, right? So I get much more information. This one is the simplest one. This is bipartite network. This part is a venue, conferences. This part are the authors. This, of course, is a projection, but I should say, even just projection, but you get into bipartite network, you can do more things. Just think about this. I show you this, and you show you these are the database conferences. These are the data mining conferences, these AI conferences, like ICML, AAAI. Okay. Why I color them in different colors? Just because I can easily partition them, cluster them. Why? Very easy. I don't need anybody to train me. I just say, you look at those authors. If authors keep publishing at Sigmod, likely we're also publishing, VRDB and ICDE. Just look at their tight links. They form a cluster. This is the database cluster, right? Because, of course, somebody also go to KDD, but it's not so regular, right? So you probably see it's nice. I just use the simple bipartite one. I can do nice clustering. I find different fields, right? So it does contain more information. That's why heterogeneous, the links contain more information than the homogeneous. You just say, I collaborate with this guy 5 times. You do not know what you are collaborating, right? Now I just show you something you may got excited. Okay. Just thinking about a DBRP as a simple example, which is a computer science bibliographic database. Okay. Now you are not looking this one as a database. You look at this one as a gigantic. Why it's gigantic? Because it's 1.8 million papers. Okay, of course you say web scale is still small, but even it's small, it shows all the components. Okay, you can see we got 1.8 million papers, 0.7 million authors, about 10,000 venues, conference and journals, and many other terms, and we never counted. Okay, but this network becomes very interesting. Why it's very interesting? You look at what things you can get. For example, I just show you a few things. Say, how computer science research is clustered. That means how many forums, how many fields, how many subfields in computer science. You will get it. Okay. And who are the leading researchers on any particular term? For example, web search. Who are the leading researchers on web search? And how those authors collaborating, evolving with time change, whether somebody quit or somebody started collaborating with somebody else. You probably know Wei Wang, who got a PhD in UCLA. You go to DBRP, we went down there in 2007. There are 14 Wei Wangs share exactly the same entry. Okay. How many papers this Wei Wang published? You add 14 together, you get a tremendous number, right? But not every paper is published by her. Can you automatically identify which Wei Wang published which papers? And we did it. I don't have time to show this one, but this one is in Xiaoxin's paper published in year 2007. Okay. And who is Serge Brand's advisor? You probably know Serge Brand, who is the Google co-founder, right? Who set up Google. But he was a PhD student in the database group in Stanford. Who was his advisor? Can you find it? When? Automatically. Remember, this DBRP has no association information. Even you do not know he came from Stanford. Okay. And can you predict with whom, okay, in the next several years, some new collaborators Christos Faloukas will get? Okay. Christos says, even I do not know. I cannot not predict. But can we predict? You probably see all those things, actually we did it, and we show there's some certain accuracy, certain excitement. Okay. So why? What we should say is, just because this integrated network contains lots of real information than the pure partitioned, projected, like homogeneous network, like social network, friends link with friends. You do not know whether this friend is your childhood friends or your collaborators on research, right? So that's the reason we like this heterogeneous, structured, multi-typed information network. Okay. Now I'm going to show you a few algorithms. It happens the majority of this algorithm actually was done by one student, Yizhou San. She's graduating this year. Okay. But I'm going to show you a few algorithm you probably find is very interesting, very exciting. The first thing I want to show you is integrated ranking and clustering together, and including classification together. In this network, what you can get. Okay. The first thing is I want to show you one algorithm she actually published in 2009, EDBT 2009, which is a very interesting paper called Rank Class. Everybody likes ranking. Do you like ranking? Okay. Remember, if I say I like ranking, I have to go trace back to the early days before Google. Okay. Early days before Google, you go to conference, you like to collect name cards. Why you like collecting name cards? Because they contain URL. That's very important. Why? Because, for example, I want to find you. How I do it? Before that, I go to, say, UCLA. Go to computer science department, and then I find you, okay? Why I do that? Because, of course, IR can build an inverted index. But if I go to Carlos' page, okay, I type Carlos Aniolo, okay, what I will find? Google may say 30,000 entries found. Are you got excited or you got doomed? Actually, before Google came, I actually got doomed. Why? Think about this. 30,000 entries without ranking. Carlos' homepage may be right in the 15,000. You think I have time to dig through? No way. Okay? So before you can automatically get ranking, I have to get a URL, which is true. Right? I got a URL, build all those links by myself. Okay, that's it. Okay. But with Google, with ranking, things changing. Okay? When Google just came out to propose, that time before Google, just proposed a PageRank. Okay. I met Rakesh. Rakesh said, you heard big news? Actually, that time I met him in UCLA because we both doing UCLA extension data mining course. He did the first half of the week. I did the second half. When he passed through me, he first asked me, did you hear any big news? Breaking news? I said, what breaking news? He said, in the Bay Area. I said, what it is? He said, PageRank. I said, I never heard of it. He said, oh, Bay Area was boiling. PageRank, that would change the whole internet search. I did not know that, but when he discussed with me what is PageRank, I also get very excited. Ranking, okay? If you can do ranking, you can do a lot of magic things. That's a Google came. Okay. But one important thing is ranking and clustering. Everybody also wants to do clustering. For example, you have so many people, you want to cluster, say this is a group doing this, the other group is doing something else. Okay. Clustering without ranking, you get a big cluster like 3,000 people or 5,000 papers. this cluster does not make too much sense unless you really rank them. But if you do ranking without clustering, it's more like you put a chicken, duck all together, say rank them. It's very hard to rank. Okay. You put database people and the computer architecture people, put them together, so rank them. I actually have a hard time to rank them. So that's the reason we were thinking ranking is important, clustering is important, but whether we can put these two things together, okay? Why we want to put them together? You think about this, okay? If you want to rank them, you don't want to rank chicken and duck together because it's very hard to rank. But clustering, people, if you know clustering, most people are thinking, I know clustering, I know at least the k-means. What they do, they put every object, they treat every object identical. They look at their space, their similarity, the distance. They say, oh, these distances closely put together. But they treat every object equally weight. Okay. Then you think about this. Okay. Suppose in computer science, you want to find the clusters in the fields. Okay. Suppose in database, say Mike Stonebreaker, Jim Gray are the big pillars, okay? Suppose Mike Stonebreaker says, I'm not going to do database anymore, I'm doing AI, okay? Things will change? Well, okay, you never believe that. But if he really start doing that, it will become big breaking news, okay? Suppose you got a first year database student come here, say, I'm not going to do database, I'm going to do AI. What things will change? Nothing will change, okay? Unless probably the only thing changes is the professor may not feel happy. That's it, okay? You won't change the whole world, right? That simply says every object may have different weights. You think about Mike Stonebreaker in database cluster weights much more than this first year PhD student, right? If he changes the field, nothing will happen, right? So that simply says we know every object may carry different weights. Why, when we do clustering, we think every object is equal or weight the same? That could be a wrong idea, right? Think about this. Now we are thinking about when we do ranking and clustering, the very important thing is if you are highly ranked, you weight more in your cluster. Oh, then you form highly ranked one will center around this, you build a nice cluster. When you do build a nice cluster, you get a better ranking. You get better ranking because it's more focused ranking, like a database ranking. You get better ranking, you get better clustering. So actually, conceptually, they help each other. That's what rank class was doing. Okay, I'll just give you a simple example. You think about this. At the very beginning for this bipartite graph, we know nothing about it, about the network or about the weights. But we can say if you are focusing, you have a strong tight on this, you get this cluster, you get a better ranking in this cluster, we get an initial ranking, then it helps you to build a better cluster. Once you build a better cluster, you look at the network, you get a better ranking, then come back a bigger refine, you get an even better cluster, then you get an even better ranking, okay? So that's the process. Automatically, you get a very nice cluster. You also get a very nice ranking. So that's the philosophy. That means we don't treat everybody equal, which actually is the right idea. Think about it. So then we work out a very interesting algorithm. A student, Yi Zhou, she actually proposed something like in EM. She got very good training on statistics. She proposed this EM-like turning around, okay? That means initially, you treat everybody just random. You say, I get a cluster, I randomly partition them. That means you can randomly partition those objects into K clusters. Then you say, I can use some ranking rules to rank those different objects. Okay. Within each cluster, you get space. For example, if you dedicate to database, you may dedicate less to AI or even less to computer architecture. You have different spreading of your weights. Okay. With this, you get distribution on this. You can generate a measure space. Then you use this measure space. You can go back to do ranking again. So this step 1, 2, 3 actually can turn into a loop. This loop is very much like a page rank. Think page rank originally you know nothing, but you based on those links, you're turning back and forth, you get a nice ranking. Okay? That's the same thing. You're turning this one back and forth, you get nice clustering, at the same time you get nice ranking. Okay? So this is the general idea. With this idea, the very important thing is how do you really do this in the network context. Okay? If you play with any network, you know network essentially you map them into a big matrix. Right? Network essentially is matrix computation. But with heterogeneous network, like we discuss only bipartite network, you actually have two types. You are not going to construct one matrix. You're constructing a few matrices, you compare them together. Okay. You can think conference is X, author is Y. Okay. Then what you got is XX is conference linked with conference. YY is author linked with author. Okay. Then XY is author linked with conference, YX is conference linked with author. At the very beginning, what do you have? At the very beginning, if you just look at DBRP, conference is not linked to the other conference. Sigma actually is not linked to VRDB. So this part actually is empty. Even this part at the very beginning, unless you co-author one single paper, you actually may have links, otherwise it's empty. And this part, you do have data. Okay. But you take this, you start turning around, you get non-empty on everything. Okay, they are linked. But the important thing is how do you set up a ranking? Okay. Ranking, you need certain rules. Okay. We actually work out two rules. One we call simple ranking, another we call authoritative ranking. Okay. What do you think of simple ranking? Simple ranking basically say you publish more papers, you rank high. For example, if you say, oh, this guy published 500 papers, rank much higher than this guy published only 5. Okay. But the same as conference. But there's one problem. Okay. You probably know. You heard there's somebody bugging MIT guys on submitting papers. And finally, they got bored. They use a random number generator generated paper. They send it there. It's accepted. Right? You probably think it's a big joke. Actually, it's a big news because even this thing, even on New York Times. The New York Times even interviewed this conference organizer. Did you read the paper? It does make sense. Okay. Of course, it does not make sense because it's random number generated. Okay. So you think you want to publish in this conference? You will be doomed. Okay. So we use this authority ranking simply say not necessarily publish more papers, you are the hero. You have to publish in the top forums, you are the hero. That's the same thing when you review the students or faculty candidates. Okay. What do? Okay. Actually, it's very simple. If you use this rule, like rule 2, you basically get it. Okay. Simply says the rule 2 says highly ranked conference attract many papers from many highly ranked authors. That one will control. If you set up a bogus conference, you say, every of my rejected paper will be finally published in this conference. Are you happy? Okay. Actually, there's one rule can bar you. You invite some reputed guys to come to submit to this conference. Do you think people will go do that? Okay. Of course, those reputed authors will refuse because this conference actually takes random number generated papers. Okay, how dare I submit paper down there? Okay, this damage my reputation. That's true. That's a golden rule. So see, using these 3 rules, actually this rule says the rank of authors is also enhanced if he or she co-author with many authors or many highly ranked authors. Simply says, if you co-author with, say, Albert Einstein, and people automatically say this guy is not simple. It must be really good on physics or something. Right? That's true. Okay. So we take these 3 rules, we actually code this one into matrix form. Okay. I will not get into detail. For example, like this one, we actually take alpha as a sliding one. You say co-author is important. We give you alpha is more, otherwise give you alpha value is less. We can using slide bar. then you probably see things will be different. Okay, we take those as a ranking rule. We just show you the process you probably can see. This left-hand side is ranking ones. Right-hand side is clustering ones. At the initial stage, when it's random, you actually get all the different colors mixed up. But using this algorithm, you go down another iteration, you look at this iteration, you probably see clearly, actually what we did is we take two big fields. One is database and data mining, another is hardware and computer architecture. You probably know if I were working on database and data mining, barely I go to architecture conference or hardware conference to publish. The same thing, the reverse is true. So we take these two dramatically different fields. You actually can see automatically nobody trained it, but after 2 or 3 iterations, the things become separated. Ranking becomes separated, different color you can see. The clustering also group into 2 corners. Essentially, it's also well separate. Okay. And actually, this algorithm is very efficient because every time when you evaluate it, you evaluate with the cluster centers. How many centers? It's how many K. You can say K is 15. You only, every time you evaluate 15 things, it's linear. Okay, essentially linear to the number of edges. So we not only get a very nice cluster, but also we get a reasonable ranking. For example, you look at this. I do not know how many people are working on theory. You look at this one, they call it theory. This one is a Soda, Stock, Fox. You know, those are typical theory conferences. You go to IR, you can see SIG IR, Multimedia C, CIKM, track. Those are the, you know, of course, our K is a little small. We take K as 15. Actually, database and data mining even not split, okay, because there are lots of people, they cross different fields. So, but you can see network like Infocom, those are different from VRDB. Okay, you can easily see the separation and reasonable ranking. Okay. Actually, if you want to do even more, for example, you say, I want to not only look at AI, I actually want to look at AI as machine learning or knowledge representation, logic, or different thing. Can I do it? Actually, it becomes hard. The reason is they all publish in HCI or AAA. Okay, no matter you do machine learning or knowledge representation, they publish in the same forum. Okay. What do? You need to introduce more. Simply says you use bipartite network. You only can do certain level, you have to stop. Okay. Now we take a little more complicated network. This is a research paper. You got a venue, author, and you also use the title, which contains terms. Okay. So if we take a paper as a center, okay, then we build a we call star network schema. Okay. It's basically you take paper as a center, you get author, venue, terms, you build a star network. Okay. And with this network, if you do clustering, you actually are not chopping the network into this is a paper, this is an author. You're not chopping this way. You actually chop them based on the connectivity. You chop them into state database, hardware, theory, those things. Actually, every cluster, you still have the star. It's more like a DNA. When you chop this one into this is heart, this is lung, this is skin, you still keep the DNA structure. That's the same thing, we keep the DNA structure here. Okay, you still, in theory, you still have paper, author, conference, you know, all these things. I just show you one thing you may not like to read, but you may like to read after my explanation. Those are the numbers. Those are what we got in the middle. Okay, how do you explain it? You probably look at this. Everything is a vector of probability distribution. Okay, you look at this first one, AAA. You know this one is an AI conference? Everybody knows. Okay. You look at which one, which column ranks high? Number 3, right? You can see this one 0.93, the other one is pretty small. You can see who are ranked high in number 3 after you look at it. Look at down, this is CVPR, this is ECML, this is ICML, this is HCI. So I don't have to run down, you know these are all AI forums. Okay, that's why in the 3rd column they rank high. Who is ranked high in the 1st column? You can see EDBT, ICDE, PODS, Sigma, VRDB. Those are database conference. They are very separated. Even it's not 100%. 0.9 probably is good enough, right? So you can see that's what we did for this. Not only that, with this magic, you actually can see this is a database one. I just show you, you can see here. How do you know this database? Because of the terms, top-ranked terms. Databases, system, data, query, management, object, relational. These are all terms for databases, right? These are the conference, these are the authors. That's what each other in Mike Stonebreaker. Okay. We can even go down a little more because you want to separate them. You can see this is what we got for XML, XQuery, they form a cluster. Those are the top authors for XML, like Serge Abitboul, Victor Vianney, these several people, Mike Carey. Those are the people working on XQuery, XML. You can see you get a nice subclusters. Okay. This one we did nothing on training. They simply say we do not use any training data. I got another student, Ming Chi. She said, why we don't use training data? We use training data. Can we do better? For sure. Why we don't use training? Okay. Her basic methodology is this. Okay. You probably only take some authors or some papers, you mark them. You say this paper actually is a database paper. This paper is machine learning paper. You say this, you give a little training. They start propagating. How they propagate? Heterogeneous. From the paper, they propagate to conference, or propagate to terms, propagate to authors, okay? Then they propagate to other authors. That means if this guy is a database guy, likely this author, the chance to be database researcher may be higher, okay? Then this author published in these several conferences likely will be database conferences. Of course, it's likely, but remember, the massive data statistics will override the noise. Finally, get a very nice result. Okay. You have millions of papers, right? So let's see. We use some kind of regularization. I'm not going to give you a detail on the math part. But we actually got a very good result. I'm going to show you. Actually, this is originally we used rank class, net class. And the student Ming Ji, she used a little training, got this GNet mine. And then later in the KDD 2011, she actually got another algorithm that is taking ranking into consideration in classification called rank class. The other one is rank clustering. This one is rank classification. You will see the magic, okay? She actually compared with quite a lot of rival algorithms, classification, very nice classification algorithm, homogeneous networks, on other things. She actually took those very highly regarded machine learning algorithms on classification. Okay. Then she actually used DBLP data, like 14,000 papers, 14,000 authors in the 4 areas: database, data mining, AI, information retrieval. She wanted to do nice classification. The result actually is very interesting. Okay. You can see this is long, wide columns. Those are the very good algorithms. People cited quite a lot in machine learning on classification. And the final 2 are her algorithms. One called GNetMine. It's more like graph regularization based on network mining. Another called rank classification. The general philosophy, rank classification, I should say, is similar to rank clustering. The philosophy is this: you treat different objects differently in classification. Okay. If Mike Stonebreaker right sit in the center, of course you do not know this is Mike Stonebreaker. You just based on graph topology. He's right in the center. He actually weights more than the first year PhD student in classification. Okay. You think it probably is right. Why you don't take Mike Stonebreaker more important than these first year student? Then you do better classification. Okay. Those results you probably can see based on her philosophy, the results actually is very good. The interesting thing is the training data actually is very small. Okay. You think about this, the training data, A is author, P is paper. You use 0.1%. Remember 14,000 papers. your 0.1% means 14 papers. You take 14 papers, 14 authors. Other people is more like doing things almost random because it's so small number of training data. How could you do things? And her actually training accuracy reached 83%. You simply say almost get the work done. Okay. And you probably want to see the real data. I just show you the real data, you probably get convinced, because she got not only nice classification results, but also get nice ranking results. You can see these are the 4 fields: database, data mining, AI, and IR. Okay. Then you look at it. If you are in database, you probably see this is the ranking on top 5 ranked database forum. Okay. You may argue with me, say, Sigmod may be even better or a little stronger than VRDB or debatable. Remember, okay, Sigmod every year take about 70 papers. VRDB take 110. Okay. Same group of authors. Finally, VRDB will be beaten by VRDB will beat Sigmod because you got the same group of authors, get more papers, it becomes even stronger. Okay, we do not have citation information. Maybe on average, Sigmod even be cited more than VRDB. It's possible. Okay, you look at that's a IR conference. If you look at the keywords, top 5 ranked keywords, it could be even more interesting. For example, IR. Everybody know IR is doing information retrieval. To see what's automatically can get keywords, retrieval information web search text. If you are an IR person, can you get better keywords than this? It's hard. Even for, I asked Chen Xiangzai, who is a top IR person in our group, in our department. He says it's very hard to get another term actually that can beat this 5, which is true. Remember, there's no human being label any term. It's all automated. So it's very good. It's human expert performance with only this few training. Okay. So that simply say ranking team up with clustering, classification, not treating every object in network equal, which actually is a very good thing. Okay. Now with this idea, we want to go even deeper to see the secret on this one. The first thing is we were thinking, we pick up in the database. We pick up, for example, conference, author, term, and the paper are most important thing to build links. And you may argue, say, oh, in DBRP, there are locations, whether this conference is in LA or is in Santa Barbara, may be important. Actually, why you don't pick it? Why you don't pick years? Why you don't pick page numbers? Okay. Of course, you say, no, those are less important. You know it. But how do you know it? Okay. If I'm blind, I'm from Mars, how could I know, okay, this page number is not important? Okay. Remember, those are meta paths. Remember your link to page, link to author, are semantic paths. We want to explore this meta paths. Okay. The first evaluating meta paths actually is the similarity. That means, how do you judge the distance between different things? You use the paths. Actually, originally, people were using the paths to judge similarity in network. People just use counts or random walk or even personalized page rank using something. Okay, I'm going to show you, like personalized random walk or something. And Yizhou Sen, she actually looked at all these. She says, all these measures may not be good. She actually got a new measure called path similarity. That means based on semantic paths, it work out similarity called path sim. Okay. And the path sim, the similarity general philosophy is this. The philosophy is you try to judge your similarity from X to Y. That means you get 2 nodes. You get a semantic path there, judge similarity. Based on how many paths going through from X to Y. Divide by the average of these 2. That means you go from X going back to yourself, Y going back to yourself. Divide by this, you get an average, or like a harmonic, those kind of average. You'll probably get a right measure. Of course, she did many experiments and thinking got this. The interesting thing is this one was published in VRDB 2011. The reason was she was challenging PageRank, SIMRank, all these done by so many people. They believe that's a golden rule. She said, no. If you want to work on this semantic heterogeneous network, this is not the right one. Okay? The reviewer every way tried to destroy his paper, okay, her paper, just because they believe PageRank, they believe SIMRank. Okay? But finally, she convinced everybody. She got a paper in the top conference rejected 3 times. She did not give up. Okay? And finally convinced everyone her method is the right one. Okay? She actually compared with the most popular used pass count, random walk, pairwise random walk, with all the well-known algorithms. Shows those are all wrong measures. Okay, that's a very bold, challenging to the authority, and finally convince all the reviewers she's right. Okay, that's the reason I just say you can't just count the number of papers. You count revolutionary idea and bold to challenge authority. Okay, then you actually can see her reasoning is the pass count just based on the pass instance and their distance. You lose semantics. Random walk tend to prefer those highly linked. If you were the star, okay, you were, say, Hector Garcia Molina in Stanford, the database, everybody point to him. Every time you find similarity, he weighs high. Okay, that's not fair. And pairwise random walk is similar thing using SIMRank. Okay, and she just showed the pass count of random walk using this idea, pairwise random walk using this idea, her pass sim using this idea. She gave lots of real examples to show her idea is right. Here we use a rare example. If you know the person, you probably will be convinced. Okay. We took An Hai Duan. Why we took An Hai Duan? Because he was a professor in our department, in my group. Okay. He was a young assistant professor. But he's a young star. He got the ACM dissertation award that year when he graduated. It's #1 in ACM. Okay. He joined our department. He got papers published. But after several years, he was robbed by Wisconsin. Okay. Now he's a professor in Wisconsin. Because we know him well, we took him as an example. Say, who is most similar? Just look at similarity. Who is most similar to An Hai Duan? Okay. Now you see the different things. Use personalized PageRank, you will get An Hai Duan is most similar to Philip Yu, Jiawei Han, Hector Garcia Molina, Gerhard Weicomb. Remember, all these people got like 500 papers published, well known. He is a young assistant professor, cannot be very similar to Philip Yu. Philip Yu got like 800 papers or something like that. Hector Garcia Molina is in Stanford, everybody knows him. You know, that's not that similar. But if you use SIMRank, you find those names. Actually, probably if you were in database, you probably recognize none of them. How could this guy so similar to the people you never know? Okay. Look at the PassSim. PassSim says, who is most similar to An Hai Duan? Jignesh Patel, Amol Deshpande, Jun Yang, Rene Miller. Do you know Jignesh Patel? Jignesh Patel was assistant professor, got first appointment in University of Michigan. After a few years, was robbed back by Wisconsin. Now they too work in the same department, same group. Is that similar? Very similar, okay? Remember, you got 500,000 authors. How do you know? We have no information about Wisconsin or Madison, right? How could we know these two are most similar? Because they publish in a similar conferences using similar numbers, all these similarity, finally get this passing. Okay. It's very interesting because she even tried, say, Yuri Leskovich, who just got assistant professor in university in Stanford. Say, who is most similar to Yuri? She actually found top 5. One is Qiaozhu Mei. You know who is he? He got a PhD in UIUC, got hired by University of Michigan, become a young faculty in Michigan. They too are similar. Is that interesting? How could you find him? Yeah, That simply says you really know the similarity, okay? So we took this. We even tried different paths. You get different similarity. For example, who is most similar to Christos phallosus? Okay. Can you tell? I cannot tell. It depends on your standard, okay? So we took one path is APA, author path, author paper author. Another is APCPAs, author path conference paper author. Okay. One you can simply semantically like a author same paper, co-authors. Another one is co-conferences. Then you can use different meta paths. Co-author APA, you will get Christos phallosus is most similar to Spiros Papadimitriou, Jim Monsan, including Yuri Leskovic. What this? These were all his previous PhD students. Because they co-author same papers, they are very similar from the co-author path. Of course, even this similarity, you look at this, the number is very different because Christos published many more papers than them. Okay? So they are smaller. But if you look at the other paths, you probably see Christos phallosus actually is most similar to me, Rakesh Agarwal, GMP Sharu Agarwal. Okay? That simply says, because we publish in similar conference and also similar number of papers. That's why even look at this is 1, this is 0.8. Okay. Actually, she showed another one is co-terms. I'm not most similar to Christos. Even we publish in the same conference, we study different issues. Okay. Then his issue, you find the co-terms is more like people working on the same issues. So it's very interesting. She actually tried Flickr. Took the lotus flower. See, which picture is most similar to this picture, this first picture? Okay, you see the path becomes very interesting. See, this path is what we call ITIs, image tag image. Remember, Flickr actually doing the tagging on all those images as a game, and the people automatically tag those things. Actually, if you just look at tag image, you probably see this lotus flower will get into similar to this flower. This one is not a lotus flower. Plus, there's a bird here. Is a lotus flower very similar to bird? No. Okay. You probably will argue. Here, you look at this picture. This one actually took as ITIG. ITIG means group. Okay. That means you not only go to the tag, you go to group as well. That means you go to single tag, group tag. Then you see all these pictures are lotus flowers. It's similar to this one. Including this picture, remember, there's nothing in common in color. Okay, this is green, there's nothing blossom yet. Okay. So semantically, you get a similarity, right similarity. So this similarity becomes the foundation. And with this similarity, she actually goes down to explore prediction. Because not only I can get similarity, I want to do prediction. This one actually was triggered by Christos phallosus. Because we took this example, showed the most similar ones to Christos. He got excited. I gave a keynote speech in Barcelona 2 years ago. He was sitting there. Then he raised hands. He says, can you predict Christos phallosus next year what paper he's going to work on? Of course, I cannot predict it because I myself cannot predict what paper I'm going to write. So I took this one as a joke. I go back to Egypt. I just say, Christos says, can you predict what paper he's going to write? She actually thought about it. She said, that's possible. I said, really? He said, let's discuss. And finally, she found the exact title is not that. It's impossible. But the topic actually is not that hard. She said, this problem is a little too easy to get another paper. She said, what about this? I predict what new co-authors Christos is going to get in the next 5 years. I said, that's even harder because you probably even do not know what student Christos is going to take. How could you predict? She says, of course, I cannot predict the young student, but I can predict the established authors who are going to co-author. I think it's reasonable. So we start doing this. Okay. That means we start doing, say, what paper next several years they are going to co-author with. And she actually got a very nice paper called Co-Author Relationship Prediction in Heterogeneous Bibliographic Network. The story is this. This time, we introduce a little more data. We introduce a citation, because remember, the co-author citation is also important. DBRP does not have citation. We actually have to get from Jietang's Tsinghua University. He gave us a citation because he got lots of data. He actually worked out this citation. He give us the data. We can do the testing. So we have venue, topic, paper, and author. Then we are studying how to predict the paper co-author. Co-author essentially is APA. So author, paper, author, you have this exactly link with the same paper. So to predict this one using all the other paths, how many paths we got? We actually say, we do not know which path is important. And we don't want to guess. We want to use data to train it. Okay. So what we do is we want to predict the APA. We just say, what are, based on the graph, based on schema graph, what are the possible paths? We actually list all the past paths of length 3 and 4, all the paths. Okay. We took those paths. We know some paths actually is a bogus path. It should be removed. But we don't remove it. We ask the training set to remove it. That means we take those paths. You probably can see the interpretation. Like this AP with this arrow PA means you author this paper cite the other paper. And that's the author of the other paper, whether you are going to co-author. Okay. This one is you co-author a paper, you author a paper, and this author actually cited your paper. Okay, whether you are going to co-author with this guy. Okay. You actually can see all these. The interesting thing is you can take some training set. You can justify which one is more important. Actually, she did it. She takes the training set. She look at those different paths. She's doing those tests. You probably know the p-value. Okay. The p-value is bigger, actually it's less informative. P-value is very small, it becomes sharp in your prediction. If you study basic statistics, you should know it. So she actually found these things. You can see this is e to the power of minus something. You probably see these are the strong 4-star predictors. This is almost no prediction. Okay. I probably can conceptually convince you this is right, because of course this is test got it. For example, this guy, the p-value is so long. Why it is not informative? You probably see. This authors got this paper. This paper cite this paper. This paper cite this paper. You got an author. They simply say you got the chain of citation. You got the author. And the author probably already retired or passed away. Who could you author in the future? Author with him? No way, right? Like Einstein, you have no way to co-author with Einstein now. Okay. So that's saying this. Okay. But why this is important, you can see. This is author published in this paper. This paper actually published in this venue. These two authors published in the same venue. The more you publish in the same venue, likely you, in the future, you may co-author with this guy, right? You can see it does make sense. So she actually used this, trying to see whether she really can do the prediction. Of course, there are some statistics thing I won't give you, but I will give you some interesting testing results. You will be convinced that actually this one works. The interesting thing is she used the real data. This is 1989 to 1995, 1996 to 2002. This is training data. Testing data actually 2003 to 2009. Remember, these data already you know. That's a fact. Okay. She basically take this part of new data, put it aside, so you cannot see it. Then I use the old data to try to predict. Then I can check how accurate it is. I just give you one example. This is Jian Pei, who was my student. He got a PhD in 2002. You can see that's perfect time. He becomes free agent. He can work with anybody, not just me. Actually, he tried to avoid me because otherwise tenure said you just still following your advisor, right? Then you can see she predicted using her past method. You can see these are the top 5 she predicted. Actually, top 5, it happens 4 of them are truths. Later he predicted that's really the next 5 years he co-authored. The only guy she predicted wrong was Osmar Zayan. Actually, Osmar Zayan was my student, was his teammate. Okay? So it's interesting is during the PhD, they never co-author paper. I actually encourage everybody co-author paper. They never co-author paper. After graduation, they become two neighbor university professors. They still never co-author paper. Okay, so that's probably the culture, right? So this must be, I don't know what's a social reason, but there's something happened. But anyway, I should say her prediction is reasonable. Okay. Actually, she predicted me. And finally, she predicted me top 10 new authors, already co-authored with so many people. Actually, it's not hard to get, not easy to predict. He predicted the top 10. 2 of them are true. Actually, Bing Liu, she predicted year 2009. Actually, we start collaborating in the year 2010. It won't count, but it's still, reasonable. Chris Pofalousas is number 2 predict. We never co-authored research papers, but we co-authored a book. That won't count because it's not in DBRP, so still fair, but still reasonable. You look at everyone and say, at least I should co-author with them, right? But anyway, she was not stopping there. She says, not only I can predict the co-author, I actually try to predict when they start co-authoring. That means that, what year they start co-authoring. That's even more difficult. But actually, I will not go through the details. She actually used logistic regression and finally found the generalized linear model is better. She actually got a very interesting thing is Philip Yu, he took as an example, say when they start citing the other one. Okay. When they start citing other one, her prediction actually on the top, like the top 7, is reasonably accurate. Okay. That means that even when she can predict. The paper actually published in the coming Wisdom conference, Wisdom 2002 in Seattle. Okay. I won't get into detail. So you actually can see that's very interesting. Then my group actually got quite a few other students got very, very excited with this and try to do other prediction. One interesting prediction is role discovery. Role discovery, this is just we supported by Army. We try to sell it to the Army. We just say, this is a communication network. It's very, very messy. Everybody communicates with everybody almost. How could you predict hierarchy? Like, if you want to predict this one is the insurgent chief, this is the cell lead, this is the real insurgent, just based on the communications, you probably will do something. You can do this. I just convinced the Army. For example, Bin Laden, okay, who you can find in the network. It's almost nothing. Insurgent, even this guy is a hardliner of Bin Laden, he will have no chance to directly communicate with Bin Laden. There's no way. Even, not to say Bin Laden was hiding, even you think about Army foot soldiers were directly communicate with Army general? No way, got scared, right? So what you do is hierarchy. If you can find this hierarchy, you're basically done, okay? And he actually, this Chi Wang, he actually used this in DBRP. He tried to predict advisor-advisee relationship and when and what period you're going to be advisor and advisee. Okay, this prediction. Remember in DBRP, there was no association information. There's no way you say when you are going to graduate, which university you come from, where do you get your PhD? No way, there's no such information, just publication papers. But based on this, he actually did, these, with all these network constructed, I will not get into detail, the prediction accuracy is pretty high. Okay. Why the prediction accuracy is very high? Actually, the rules he used, knowledge he used, is very simple, very plain. Everybody will take. For example, he used the advisor has more publications than advisee at the time of advising. Agree? If you publish much more paper than your advisor at that time, you probably will not find him to supervise you because you better supervise him. Right? Then another interesting thing he used is once advisee become advisor, will not become advisee again. Agree? If you become professor, do you want to sneak down to follow somebody as a student? No way. Right? So that's the simple rule. But remember, this rule will propagate. It's like PageRank. We'll start propagating and turning around. It become powerful constraints. With this, I just show you the several examples he showed to me is really convincing. If you work on machine learning, you probably know David Blake, who is a young star now in Princeton. Okay? Who was his advisor? Okay. And our system find two. One is Michael Jordan, who's in, actually we did not know which Michael Jordan. Of course, you know it's in Berkeley. Another is John Lafferty. Okay, he's in CMU. Okay, now it's not in CMU. But even a year actually was not too far. The real thing is, this is his PhD advisor. This is his postdoc advisor. Okay, that's the year of advising, that's the year advising. Actually, you see, the real fact is not too far away. This is 2004, this is 2006, you probably can see. And the student actually used my own student, Hong Chen. She got a PhD from me in 2008, and now is assistant professor in Chinese University in Hong Kong. Actually, we found two advisors. Finally, we find one, Chang Yang, actually was her master advisor. I'm her PhD advisor. The year is all very close. Then we took Serge Brand, who is Google co-founder, say, who was his advisor? And we found Rajiv Modwani, and that's the year of advising. You probably would agree, because it's really Rajiv Modwani actually got a lot of share of Google, you probably know. And also, that's the year, but with such a short year, probably did not get PhD. That's also the truth. Right? So it's a reasonable prediction. So then we actually finally, I got another student got excited, say, with this, what about we integrate the information network of DBRP with the real web, academic web. Okay. That means you take DBRP data, you want to integrate with the real web data in all the universities. Okay. You can find, if you want to do multimedia mining, you want to find which university in which location is a hot top ranked one. The important thing is web, everybody can construct something. It's almost scattered. It's like a free agent. You can do anything. How could you mine these web structures? Okay, so that's interesting. That means what he wants to do, this Tim Wenninger, he wants to say, give me one professor homepage. I try to find all the professors in the same department, all the homepages. No more, no less. Okay, that's computer science. What he found is, actually, web is not randomly constructed. Web, the space allocated, was randomly structured. The key is how to find it. He actually linked those structures with the different entities and then formed a path across several HTML or these kind of structures. He actually can identify the right path and the right, you give me one, I find all the remaining ones. Okay. The interesting thing is you probably can see the accuracy. That's the very interesting thing is this. Okay. He actually found, he went to US representatives, the government, the senator, and the representatives. He found all the committees, all their senators and the representatives, no more, no less, just using the structure, find everyone. Okay. The interesting thing is he actually found more. He found actually the committee are two. One is Republican, one is Democrats. They are on the web. The only thing is when Republican got a majority, all the Republican things become visible. But the Democrats actually have the same structure. They are not visible. Okay. But he actually found them. He found anytime when the election, like November or something, they turn around, all the web page become visible, the other guy become non-visible. Okay, it's kind of magic, but he found all of them. But the problem actually is computer science. You probably know the computer science is tough most. Why? Because everybody is kind of a hacker. Okay, you get a computer science. He actually used computer science, CS faculty, UIC ones. You probably see the CS faculty with 25 computer science department. He never got a 100% recall, 100% precision. The reason is the computer science faculty put their homepage, some put in the Facebook or LinkedIn, some put in some very weird place. You just cannot find them. So he finally found this 96% recall, 82%. Of course, he's still trying to improve. He said, the topmost one are the computer science guys. Every other guys is so tiny, so tidy, okay? So that's a good lesson learned. But with this lesson, actually he was doing structure mining on the paths and also mining the parallel structures. For example, you want to find the information on all these. You are not mining one web page. You get 50 faculty in this department, you mine collectively. Actually, they enhance each other. Then the structure is much easier to be discovered. Okay. So I will not give you a very detailed because we got to run out of time. What I just conclude this one is this. Okay. The first thing is I say heterogeneous information network actually is ubiquitous. It's almost anywhere. You are not thinking this is rare to find any database or anything like a semi-structured, even unstructured, like a news network currently we are mining. You can construct the heterogeneous information networks. The more you construct it, the more structured, the more information you can dig out. Another interesting thing is structure can be progressively refined. If you get this network, you can find different way ones, you can separate them. Okay. And very rich knowledge can be mined. And also there are much more to be studied. Okay, so that's the general information. There are quite a lot of papers. The first one, actually, this student also got excited. She actually is co-authoring a book. Because of the PhD time, you cannot write a thick book. She is writing an e-book. Contacted with this publisher already. We got to sign a contract. She got a half of the book done. The book is just like 100 pages. It's not like 500 pages. She will never finish her PhD. Okay. So that's the one. So I gave a talk in Grace in Athens this September. I took a nice picture. So it simply says, you actually can link to the past. Thousands of years ago, it could be a network. Okay? Thank you. Yeah, anybody got any questions or comments?
Well,
yes, I see the. Yeah, that's interesting. In the real social network like Facebook, actually the Facebook, why we did not get into Facebook, the first important thing is it's hard to get the data. Okay. Remember, the Facebook actually hiding many things. What you see is your friend. Even your friend, some friend may prefer not to publish something. Okay. So the Facebook try to get these kind of heterogeneous network, get lots of related information is very hard. Okay. That's the reason we did not really jump into Facebook or LinkedIn to do the mining. But in principle, okay, Facebook, you also can classify your friends into different groups. It's like patients and doctors or advisees. Then you reconstruct this network from the heterogeneous typed way. Then you can mine something interesting. But we never try it. I did have a student, she actually joined Twitter. She did some mining in Twitter company in the summer intern. She found something very interesting. Okay. But I could not tell because they want to keep things secret. Okay. Yes?
I'm very interested in prediction. It's like you go to a fortune teller and tell you what the future will be. But you just showed us some sort of example, very well structured, who's going to co-author with. But in general, because it's very well structured, so you can do something with inferring and things like that.
Yes.
But suppose things are not as well structured.
Yes.
then you don't know how good is the prediction.
Yes, that's true. Actually, the power of this one, I actually got it fall out. The power of this one actually is structure. That means if you get more structured information, your whole thing becomes more organized, you are more intelligent. Okay. For example, just to give you a simple thing, we currently are mining news network. The news network, we have to use like a natural language, processing, information extraction, all these tricks. Because you get more things structured out, your network become more informative, then your prediction, your clustering become better. Okay. If you treat all these as a flat, for example, in the news, if you find this is the presidential, like a Romney, this is a candidate, this is a voter or some commentator, and you know they are different. One is a candidate, one is a commentator, or this one is an issue about, say, abortion or something. You know they are different categories. You link them together in typed network. You are much more informative. You can do something better. But if you just think those are people, they are all linked, actually it's very hard to do prediction. You even do not know they are presidential candidate. You can say, I'm the presidential candidate. The people will laugh, right? Because, yeah.
Usually people like prediction, they would like to see how accurate would that be. That's a 50% probability, 70% probability would be correct about that. In your case, you just showed the two poles, you know?
Yes.
And so those most likely that, you know, but you don't give out any sort of probability. So in this case, you said this is so much better than others, you know, that's what you're saying. But you don't really provide any quantitative. Of course, it's an extremely difficult question. You know?
Yes, yes.
Of course, you say fortune teller, you know, and we'll tell you when you're going to do this, when you're going to do that. Only when you later on you look back, you know, see if it's true or not.
Yeah, actually, you can see we predicted the co-authors. We only do the top ones, not the bottom ones, because of the bottom ones very, very hard to predict. For example, who in the next 5 years, which student are going to work with you on what? It's almost impossible. But you predict the top ones are usually the mature authors. Then you predict it's reasonable. There's a boundary. You just cannot predict everything. Yeah, otherwise, I don't have to work. I go to stock and say I can predict it, right? So that's impossible.
But some people do have the foresight, you know?
Yes.
So out of that, each season, you know, equal
Yes.
weights you have. You should invest in this, invest that.
Yes, yes. It's interesting. Just to give you something, you say, there's something sounds very, very hard. Actually, with this network, you can do better.
Yeah,
Okay.
more structured.
Yes. Yeah. Yes?
I'm at AI with your first contribution that you have ranking together clustering.
Yes.
To me, it seems somehow related with this LDA, like David Blake. You have the clustering, and even the clustering, you have the dictionary that have the words that you have the probability.
Right, right.
How is it clear how this is related to your work?
Yeah, actually, you probably see we do this rank clustering.
EM, right?
Yeah, yeah. We actually using this EM algorithm. We believe you can use LDA or many other different kind of clustering algorithms. The key innovation is you use network structure, but you don't treat all the objects equal. Okay. And also you use typed information, use multiple linked typed information. You don't treat all the different type things equal. Then things will happen, become smarter. I think that's the major difference. For example, we compare with a few very competitive machine learning algorithms. Actually, most of these algorithms were doing classification on homogeneous networks. But now we have a heterogeneous one. Simply says you try to predict it using homogeneous algorithm, try to predict a heterogeneous one, it's almost impossible. So that's the new thing we think. Once you treat heterogeneous as homogeneous, you lose lots of information. Sometimes you even do worse.
I'm just trying to understand it somehow because now they have some called generative model.
Yes.
To generated data, and
Yeah.
it's not homogeneous. You have different nodes,
Yes.
and each node is generated some kind of instance of.
Yeah. Actually, that's a very good question. Remember, there are, I should say, 3 philosophies. One is you treat everybody as same type. Another one say you treat everybody as different type. Okay. We are actually different from both of them. Okay. We are treating, there are several types. You belong to author, you belong to paper, you belong to keyword. These are 3 different types. Okay. We do not treat everybody as a new type. Then simply says authors all cluster into authors. That's one type. You actually make use of this information. There are people, you study some network, like they study WordNet. They treat every network, every word is different type. So you get 3,000 words, you have 3,000 types. It's different from this philosophy. Yeah. This is a very good question. Yes?
But by the definition that you know only have 3 types, that contains a lot of knowledge in there.
Yes.
But in fact, it could be generalized into 6 types.
Yes.
And if you do a job properly, you should be better than 3 types. And vice versa. If you didn't do a good job, you end up with worse. And how do you do that step?
Yeah, that's a very good question. The first thing is you may get multiple types, but some type is more important than the others. You finally will be able to find it. You can see we used many meta paths. Okay. Some paths is more informative, we use it. Some we just drop it because this type is not important. Okay. But on the other hand, is originally how do you get this type? To get this type, of course, you have to have some seeds. You get this type. With the seeds, you use network, you can progressively refine the type. Okay, just thinking about this. Suppose you know Romney is a candidate. Okay, then you suppose you know Ron Paul is candidate. You don't know others. But you start building all those networks, you may find that actually this Centaurium or is Gingrich actually also candidate. It's possible because they have similar structures. Then you find more, you do better. Then you say, I'm the voter, I'm not in the same category because the link structure is completely different. So you can see, if you know something, you know the network structure, you can, it's like a page rank. You can progressively refine it. Okay.
That's the one last question, please. Or okay, otherwise we should take it.
Okay, thank you. Thank you very much.
Everybody was, listening to the end. Normally you see few people leave. Everybody was
Yes, yes.
One away, but it was very interesting.
Okay.